Hello, everyone. I am so happy to be here. I mean, this venue is amazing. Didn't Braga do an amazing job with this theater? Like, come on, this is amazing and beautiful. Yeah, clap. Yes. So I'm Davy Stevenson. You can find me usually at Davy Stevenson on most things on the internet. I very recently joined GitHub as an engineering manager, so I'm pretty excited about that. I work remotely from Portland, Oregon, and given Kylie's talk yesterday, I figured I would go into a little bit more depth into one of my favorite cities ever. So Oregon is on the far west coast. Usually people are like, where is that? I don't know. We're like, it's on top of California, and they're like, oh, okay, I got it. I also spoke at Baruco a couple weeks ago, and so I know there's probably a few of you here who saw my talk there, so if you're watching it for the second time, thank you very much, and now you get to learn about Portland too. But from Barcelona to here, I decided to take a road trip and drive across Spain. And while I was doing that, I was thinking to myself, well, it's like, what is actually the comparison of the size of Oregon to the size of Spain? It seems like they might actually be comparable. And a lot of people don't realize just how enormous the United States is. And so this kind of gives you a little bit of a hint. I found this site that will compare two places on a map and keep the scale the same. So Spain and Portugal together are, of course, larger than Oregon, but not by that much. So Portland has a slogan called Keep Portland Weird, which they did steal from Austin, Texas, I will admit that. But I like to say that we are weirder in that we have this fine character. He's known as the Unipiper. I've seen him like 6 or 7 times, sometimes on, because the unicycle is common, but he also has a solo wheel, which is very interesting. Sometimes the flaming bagpipes, sometimes not. But if you think it's just a one-time thing, no, he definitely is around. I also really like the fact that the Portland sign, I don't know if you can see it, but at Christmas time we put a little red light bulb up there to make him a little reindeer. I love Portland. We also have the world's tiniest park. So this is officially a park in the middle of a median between 2 streets. And I like to do my own part to keep Portland weird as well. This is my cat, Kamaji, and he likes going for walks and is pretty much generally the most awesome cat ever. There is also a TV show called Portlandia, which I do not consult for. They should reach out to me about that one. But it's parody for the town and city of Portland, Oregon, and it's frighteningly accurate for anyone who's actually watched it. Who does watch Portlandia at all? Yep, okay, great. It is scarily accurate, so don't think that that's not true. And just in case there was a little bit of the joke that Kylie made about putting a gem on it went over anyone's head, this is what it's referencing, which is a skit where Carrie and Fred are joking about the plethora of putting bird-related items on every single tote bag and hat and skirt and pin that you can find in all the cute shops all over Portland. This is my favorite GIF about it, putting a bird on some toast. And I thought this would also be quite relevant because here in Braga, I have been seeing the plethora of roosters. I've already bought at least 3, and I might buy more before I leave because they're very cute. So I thought that was another similarity between Portland and Braga, our love for birds. Okay, so now on to actually talking about the title of the talk, which is orders of magnitude. And what that really means is I'm going to be talking about numbers. Really, really big numbers, really, really small numbers, and all the numbers in between. And more importantly, how our brains are good or not very good at understanding what these numbers actually mean. So number sense is the idea that certain animals have intrinsically within them the understanding of certain numbers. And there are a lot of animals that have been proven to have number sense. Some of them might be not very surprising, like elephants, dolphins, whales, great apes. There are also animals that you might be a little bit more surprised to know do have number sense. Crows and some other birds can inherently count with small numbers. And even insects such as bees and ants have been known to be able to do rudimentary counting. And what this really means is, of course, they don't have the ability to tell lots of different numbers apart, but they can tell the difference between 1 thing and 2 things, 3 things and 4 things. It usually breaks down around numbers 5 and 6. And then, of course, There's also some capability of distinguishing differences between larger numbers, between like an 8 of something and a 13 of something. And humans also, probably not surprisingly to everyone here, do have number sense. Babies can tell the difference between one thing and two things, and you can make experiments that show that babies show surprise when something disappears. If you show them a pile of 3 things, put a screen down, there's 2 things left, they show surprise because they expected there to be 3 things. But the thing that might be surprising is that our number sense isn't actually any better than that of most animals. We still have a hard time telling the difference between numbers between around 4, 5, or 6. And this is shown by studying a lot of some of the tribes out there who still haven't discovered things like finger counting or general tally counting. So the first lie that I'd like to state is that our brains inherently understand numbers. And this is true at a very small scale, but more broadly speaking, it is not true. Our brains aren't very good at numbers. We're born with number sense, but we have to learn how to count. So, as I mentioned, one of the first ways that human tribes learned about counting was using their fingers. And learning to count was really only truly advantageous once humans had discovered agriculture and farming, and they had something to actually count, such as managing livestock. In addition to finger counting, they commonly use stacks of pebbles to correspond to the numbers of animals that they might have, tally marks on sticks, or even knots on rope. And humans that don't yet have words for various numbers can still keep track of things like their herd of sheep using counting in this way. So have 8 little pebbles in my pocket, and I can keep track of my 8 sheep, even though I don't have any words for any numbers at all. So once that we had things that needed to be counted, the next, of course, logical step is to create names for the numbers that correspond to the numbers of things you might have. And it's because clearly easier to say, I have 8 sheep, than to dump out the pebbles from your pocket in front of someone and say, I have this many sheep, right? That seems like a pretty good advancement from that point on. And the very first types of counting that a lot of tribes came up with was the one-to-many. That was kind of the first step. And this is the type of counting that's still very prevalent in some tribes, such as the San people of Namibia, some various Aboriginal tribes in the Amazon rainforest, and in Australia as well. Still have the limit to their coming up with names for numbers is around 1, 2, and many. And then the next step that many human civilizations came up with was lots of different names for lots of different numbers. And an example of this is the Tsimshian tribe. This is a tribe in British Columbia, up even further north than Oregon, up the western coast. And this tribe had different types of numbers for the different types of things that they were counting, such as, if you're counting men, that's going to be using a different set of words for the numbers than if you were counting canoes. I also do really like that there was, different even numbers for long objects and trees, and then canoes just has its entirely separate category, right? Because canoes are really important if you live in the coasts of British Columbia, I guess. And before we talk about how silly this seems to have generating so many different names for different types of numbers, is that we have this history embedded in the English language itself. So these are all words that really mean 2, but we came up with different words depending on what type of thing there was a pair of. And so that comes to another lie, which is counting things and coming up with names for counting things is easy. It's not. It's actually very difficult to discover abstract number counting, and counting takes a lot of mental energy as well in order to be able to count the differences between different numbers and what exactly you're counting and what to count. Think about trying to count fluids and volumes. That's a whole different problem. So now that we have some names for numbers, we want to create some numeral systems to encompass how to represent these numbers in written form. And one of the first, actually I don't know if it's the first, but one of the ones that we can talk about here today is the Roman numeral system. And this is an improved tallying system. So similar to the notches on on a stick. We have 1 is just a single slash, and we have v is 5, x is 10. And this is also, interestingly, a positional notation system. You can see here that all of the 1s are on one side, and all the bigger numbers go off to the left here. And there was a slight invention that they came up with to augment this a little bit, which is the subtractive notation, which is like in this case, where they placed the C after that one M to denote that they wanted to subtract 100 from 1,000. And so, of course, there's still kind of a problem with this type of number system, right? Like, can anyone tell me what that number stands for? 1927, but it takes you a little while. You have to count it. 28. Sorry, Sam. See, counting is hard. It's still very difficult to kind of tally these up and do this summation in your head when dealing with the Roman numeral system. Next up, and much more successful, of course, because we're still using it today, is the Arabic numeral system. And in this system, each numerical value in the number base gets its own character to represent it. So since we have 10 fingers, we chose 10, so we have 10 digits. The other really interesting thing that came along with the Arabic system is positional notation. So this is, of course, different than the Roman system, where in this case, the sequence of digits denotes different things depending on what position it is in the number itself. And once we have positional notation, the concept of exponentiation comes really quickly after that. Now that the digits have a place, that place itself can be counted. So now we have something like 100,045, and that can be represented as 1 times 10 to the 5th plus 4 times 10 to the 1 plus 5 times 10 to the 0. Or you can also use the E notation right here to compress the way we're describing the exponents. And I'm going to keep using this notation because it's a lot shorter and doesn't require me to have to highlight and do superscript and keynote, which is really irritating. So that was enough of 10 to the... And so now that we have these exponents, since we really love naming things, we're going to name things again. And because we love naming things multiple times, we're going to name them multiple times too. So now we have a lot of different words to describe the different levels of numerical exponentiation that we have available to us. And so what number systems really do is allow us to count larger and larger numbers, and not only that, but to be able to easily express and tell another person what that number is. My computer is 3.5 gigahertz, right? That is a very compact way to express a very, very large number to someone in a very short amount of time. But there's a lie inherent in that, which is that naming these numbers allows us to understand them. Like, understanding the scale of 3.5 gigahertz is still a lot beyond what our brains are able to conceptualize. So what I've come up to so far is that we do have number sense, but that only encompasses numbers 1, 2, 3, 4 approximately. And counting is actually surprisingly hard, and that naming doesn't actually mean that we have an understanding of what those numbers mean. And so how can we use this to help us become better programmers? So there's one way we can do this is within our layouts. Blocking things out into very explicit sections and not having too many of them, like the common 3-panel layout, is one way that we can take advantage of humans' inherent number sense to be able to easily grasp where they should be looking on a page to find information. Similarly, you might have a whole collection of numbers that you want to be able to provide information to your user. You could create a table of number data, right? You could do that, but what's a lot better to do is, of course, to figure out how to visually represent this information, because just seeing those numbers isn't enough to have people understand it. But if there's a trend in there and you want to be able to show it to them, then that's a way that they can understand the scale and what these numbers actually mean. And this can also help us when we're writing our code, too. One of the things we talk about a lot is keeping our method, the number of lines in our methods short. And this also ties back directly to being able to understand and grasp in our heads very quickly a small set of numbers instead of having to have a huge 1,000-line method, and where we have to really spend time thinking about what each section does and trying to remember all of those different sections. And this also applies to tests, of course, as well. And I think there's a corollary to this, right? Dividing things into tiny, tiny methods is good, but there's also wanting to be able to understand the hierarchy of how objects link to each other. And having deep inheritance also has a similar sort of problem in our minds, where it's harder for us to keep track of the links and know how they're all connected together. And instead, if you have a set of code that you're trying to debug or work through a flow, it's a lot better to be able to do that if you only have to open something like 3 panes instead of 15. So in order to talk a little bit about what really big and really little numbers mean, I'm going to first define a baseline for our human experience. And I'll do that for both distance and time. So I'm claiming that a baseline for distance or size is about 1 meter. That's approximately the size of our bodies or our arm reach. That's kind of the way that we experience the world, is 1 meter at a time. So what is the smallest thing that a human eye can see? And that's approximately the size of a human hair, which is e to the negative 4 or 1/10,000th of a meter. What's the very largest thing that we can experience? And I'm going to claim that that is a mountain. A mountain is something that we can both see from a distance and grasp how big it is, and yet it's also something that we can still actually climb, right? We can still go up and touch it, we can still climb to the top, still experience the entire thing in the way that we can't experience something like the moon, for example. So what about time? I'm going to claim that 1 hour is a good metric for time. That's oftentimes how we kind of divide up our day into hours or half hours, but that's a good, decent amount of chunk of time. And so in that sort of realm, what's the smallest thing that we experience as humans? And that's about a blink of an eye, which is again about e to the negative 4. And the largest thing that we experience is, of course, our own lifespan. I like that this number is a little bit bigger, e to the 5, yay! So we get about 100,000 hours of time. Oh, that's kind of depressing. So skip right over to the next lie, which is that we as humans have a lot of direct experience with very, very large or small numbers. And the fact of the matter is that's not really true. From the amount of things that we can experience and interact with, our scale is pretty small. It's actually from the width of a hair to a mountain, or the blink of an eye to a lifespan. And this is in the thousandths to thousandths range of numbers. So humans long ago discovered that curved, clear surfaces are able to magnify and sharpen images. But for a long time, we didn't really understand the mathematics of how that worked or how to control the refraction of light. That didn't stop early humans from using this knowledge to try and create lenses to try and see more of the world. This Nimrod lens is one of the oldest discovered lenses in the world. Dates to 750 BC. And lenses like this have been discovered in places like Egypt, Assyria, Greece, and Babylon. These lenses are still pretty crude. They do some minor magnification, but it's not very complex, because the mathematics of how to actually create the correct curved surface wasn't around yet. So optic theory is the study of this bending of light and controlling its how to converge and deal with the refraction of different colors and all of these things, to be able to create lenses that can magnify things at various levels. And the law of refraction was required to be discovered before humans could very successfully converge light to a single point, which is required when we want to invent something such as a microscope, which was invented in 1590, and the telescope soon after, at 1608. And so it was at this point, really, that we had a way of expanding our world much more drastically than we'd really ever had before. And so now, like today, what are some of the things that we know about going back to our 1 meter baseline? We've gone much, much smaller than the width of a hair. We've discovered bacteria at e to the negative 6. We've created microprocessor memory cells, which themselves are e to the negative 8. The current smallest gate length is e to the -9. This is pretty fascinating. Surprisingly, and a massively tiny thing. That's the gate length of a 16 nanometer processor. And that's pretty amazing when you consider that atoms themselves are at about e to the -10. The diameter of a silver atom is 153 picometers. So that's, we're converging on creating things that are the size of atoms themselves. And then we've also been able to study things even smaller than that, such as the electron at e to the -15. We've also been able to explore the world in greater detail, well beyond our own solar system, around our planet and into the solar system and beyond. So the moon is at e to the 6. We have the sun at e to the 9. And the sun isn't even that big of a star. We can see here, it's real tiny. There's the sun. So compared to the blue supergiant Rigel at e to the 11 and Betelgeuse, the red supergiant at e to the 12, the sun itself is even very, very tiny. And because I was an astrophysics major, we got a quick astronomy lesson, because I love Rigel and Betelgeuse and love that they're so close together, in the sky. So we have Betelgeuse here in the shoulder of Orion. Rigel is down as its foot. And these are two of the brightest stars in the sky, and they're also near Sirius, which is the brightest star in the sky. So if you ever want to be able to easily find some really bright stars and know their cool names, now maybe you can find it. We've also been able to see even larger things than that. So this is the pillars of creation, which are only a small subset of the Eagle Nebula. They're so named because this cloud of gas and dust is currently creating brand new stars within them. And the side pillar to the left is about 4 light years in length, or e to the 16. So going to time, we've also been able to experience things much smaller. Discovered that the synapse of our brain is about e to the -7. The processor cycle in 1980, and that's 5 megahertz, that already was e to the -10. And the current 3.5 gigahertz that I referenced before, that's e to the -13 in time, which is fascinatingly tiny. I mean, this is like the size of electrons in size from meter to electron is almost the same as from 1 hour to a single processor cycle of our computers that we just have today. We've also been able to discover and learn more about how things happen in much broader timescales. So 5,000 years is the lifetime of what is kind of considered now to be the longest lived organism on Earth, which is the bristlecone pine at e to the 7. And that compares to the length humans have been around at e to the -9 is about 200,000 years. And that pales in comparison to how long dinosaurs roamed the Earth at 100 million years, or e to the 12. And so that was a really long-winded and pretty pictured way to say that we haven't really been experiencing the world in great detail for very long. That's only been about a couple hundred years since we've been able to kind of expand beyond what we can experience just as a single human. So the other thing that I'd like to tie in with this is that humans, our brains are trained to be able to try and estimate the odds. And one of the most important things around this is to be able to determine risk to our lives, right? This is kind of important for organisms to have developed this talent. And we have a problem, of course, in that we prioritize immediate risk over long-term danger. We can see this in ourselves, that we're terrified of snakes and shark attacks, and yet go driving around in our cars daily and continue to smoke cigarettes, even because those feel safe. They don't feel the same amount of danger, even though they're still much, 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 much more dangerous than wandering in a field and getting bitten by a snake and dying. So that's a quick way to say that our brains are really bad at estimating risk. And we've also, this ties into a lot of the other talks we've heard today, right, where it has to become an emergency before oftentimes we can prioritize the things that we need to do to our code bases to save our products and projects. And this lends itself to some errors in our thinking, right? We think things like this. There's no way that a user is ever going to do this. Or it's absolutely impossible for two users to be clicking this button on the exact same time or trying to trigger these two actions at the exact same time. Or even like lower level, there's absolutely no way that in this giant 100 or million line code base are these two lines of code going to be executing at the exact same time. And the problem, of course, is that that is entirely false. That is our inability to understand very large numbers combined with our difficulty in correctly dealing with risk assessment, telling us that those are very uncommon things, when instead, when you're dealing with things at scale, those things become almost a certainty. So real things to remember when dealing with computers is that extremely large small numbers are new experiences to humans, and that calculating the odds of something actually occurring is surprisingly hard. And so this brings us to things such as the dreaded name form. So this is one of the people with the longest provably legal names. You can barely read it. So of course, this is a German fellow. So he had 26 given names, one for each of the letters of the alphabet. And Z just ends like right here, right? So then this is his last name right there. And he has a senior too, but that barely adds. So that's his last name. He went by Hubert Wolfstern. But this fellow actually existed. And do you think your web forms are going to be able to handle that guy if he wanted to sign up for your service? And then there's also people with one legal name. And we know about some of these cases when people legally change their name to one legal name, but there are people that are just born with one name. It's common in the royalty of both Indonesia and Japan that the royal family only has one name. And if the Emperor of Japan wanted to sign up for your service, you kind of want to have that be allowed. You don't want to make him put Emperor in the first name field or something like that. And then, of course, there are more complicated things, such as people with hyphenated names, dealing with Unicode issues, and then I am pretty sure that pretty soon there's going to be the first baby with emoji in their name. It's going to happen. It's going to happen, folks. We've got to be ready. And this, of course, email is one of our other favorite examples for this sort of thing. It's always very irritating for people who like to take advantage of the filtering mechanism on Gmail, add the plus to be able to easily filter out the spam mail you might be getting for signing up for certain things. And there's a lot of web forms that just do not accept plus in the email address. And then, of course, now that we have an explosion of fancy URL domain names, that's another thing that can be really difficult for websites to be able to handle. And those are just really tiny things. This was just copied and pasted from the examples of email addresses from Wikipedia. So these are all valid to the email spec email addresses. And so being able to deal with people with these types of email addresses, and this is where, how many, there's some of you out there saying there's no one with that kind of email address. Well, there are. You have to know that someone out there is going to have ridiculous email addresses like this. And that's kind of really only a start. This is just kind of input validation. But this comes to a much broader story around things such as being able to use mutexes correctly to prevent the same line of code from executing at the same point of time, using database transactions to correctly and in all ways to ensure that data is maintained properly, and using background jobs and things like that correctly to push off processing away from your web form. And we all know about these things, right? There's I bet everyone here has touched at least two. If you're using Rails, we all know database transactions. We've at least used a couple of these in our day-to-day jobs. But it's still something that is a big problem and bites us in the hiney all the time. It's still a really, really hard problem. So in conclusion, it's really important to realize and understand that the human experience has expanded drastically in the last 400 years. We've gone from experiencing the world in the thousandths to thousands range to being able to experience the millionths and the millions, to the billionths and the billions, and to the trillionths and the trillions. And to really remember that to build scalable code, we really must be developing right from the start for that millionth user, for the billionth request to your web server, and for the trillionth event that you might be processing. And when you're working in this sort of world, the important thing to remember is that the edge case is in fact the certainty, and you can't make assumptions about the types of things that are going to be happening and the types of users who are going to be using your systems. Thanks.
I'm curious about the process you took to research for this, because did you have a point when you started like researching and digging through the whole information, or did you start like reading about numbers, you ended in dinosaurs, and then thought, hey, there's a point in all this?
Yeah, I mean, I think a lot of these things are, things I might have like known a little bit about. And when I kind of came up with the topic of like really trying to learn more about big and small numbers, I did start doing a lot of researching, and that's kind of when the counting and number section at the beginning was only supposed to be like a really tiny prelude, but I was fascinated by it and was like, oh my goodness, like I'm so excited by like learning more about how humans themselves kind of generated like counting and numbers that I just kind of kept on going down like a Wikipedia research hole for like a couple days, and then kind of emerged with expanding that section a lot because I thought it was so fascinating. But then, the original idea was definitely around big and small numbers and really trying to lay those out in a kind of a scale that could be comparable in some way. So hopefully I did that.
Hi. In the previous talk, we heard that you should aim for the 80%, like pitch your products at the 80% and not worry about that last 20.
Mm-hmm.
And then there's also the conclusion there that the edge case is a certainty. And I'm wondering if you think there's a conflict there and whether there's some, I don't know where I'm going with that question. Is that a conflict that you see?
Yeah, there's definitely a conflict there, right? And I made very bold statements, but in most cases, it's going to be very, very difficult to at all times, code for the edge case. There's going to be cases in which we're going to have to like make decisions on what the priority is. Really, what I want everyone to take away with is just kind of keeping that little person in the back of your mind telling you and poking you when you have to make those concessions to actually get something out the door, to remember that that's still something that's going to happen and still something that should be addressed sooner rather than later, so that you don't get yourself into a tight corner that is something that's going to need a major refactor or something to get out of.
Yeah, thank you.
Mm-hmm.
What I meant with the 80% was that it's usually truly enough for the stuff that we do,
mm-hmm.
but it always depends on what you're doing. If you have 1 billion requests per day, then the edge case happens 5,000 times a day. So this is what you should work for.
Yep. And even if you're going for 80% of the millionth user, that's still 800,000 users, or some large, see, I'm going to do bad math. Anyway, 80% of a million is still a really big number. So even cutting out that 20% still encompasses a lot larger of a scale and scope of people than you would otherwise.
Yeah, and plus what you already said, if you say 80% is enough, you shouldn't pretend that the other 20% don't exist. You
mm-hmm.
should keep in mind that eventually it will blow up in your face.
Yep.
But sometimes that's okay.
Yes, sometimes that's okay, because you need to get something out now so you can start making money, because that's also important. Everyone loves money.
Well, I'd just like to add a small factoid, that is, the human being started to write in order to represent numbers. This was what you missed to say, and it's... And additionally, I also have a question that is, does the flaming bagpipe actually sound like anything?
Yeah, he's bagpiping. There are some videos on YouTube. I didn't embed them into my talk, but there's actually a really famous video of him unicycling with the flaming bagpipe and playing the bagpipe in front of the Keep Portland Weird sign. So that one's really easy to find on YouTube. Okay.
I think we're good.
Mm-hmm.
Davy Stevenson.
Thanks.